Hello everyone. This video will briefly cover ridge regression. If you've began to study linear regression, or linear models, you may be familiar with linear regression already. Ridge regression is another type of linear model or different type of regression that is often compared to linear regression. And I will take the next minute or two to briefly talk about what ridge regression is. And in a separate video, I will do a comparison between linear regression and ridge regression. So first up, ridge regression, while similar to linear regression, they are similar in the sense that for the most part, they use the same equation. So if you've studied linear regression or have watched my previous videos, you may recognize or recall that the formula for linear regression looks a little bit like this. You have y hat, which is your predicted value from your model, which is equal to W, which represents your weight matrix, multiplied times your input feature values, or X, plus some kind of bias or offset. Okay, this is linear regression right here. Ridge regression introduces a new parameter called alpha, which is added to this equation, but as a means of controlling essentially how much power your weight matrix has, right? It's another way of incentivizing your model to perform or behave a different way as opposed to just linear regression. I mentioned in the previous linear regression video that the metric used to calculate where your model performs best using linear regression, mean squared error does not actually have a place in this formula. And that means that while it is used to calculate where your model performs best, it's not a part of the model. So we use this alpha parameter in ridge regression in order to change that. So as I mentioned, the regularization parameter alpha, this applies an additional constraint on the model, which helps improve generalization. Why does it help improve generalization? That's because in a linear regression model, all of your weights, remember weights are something your model learns, all of that is based exclusively off the training data, right? The model will only learn off of the input data, and that will train the weight matrix to perform however it does once you try to deploy it. However, the alpha parameter, let's say alpha looks like this, it is scaled with the value of the weight matrix. This isn't the full equation, it just looks a little something like this, so I can keep it simple. So you can imagine, actually let's do this instead. Let's take this, let's grab this, bring it down here, make it a little bit smaller, and add an alpha multiplied times the weight matrix. Now, you might be asking, how exactly does this really change the equation here? Well, as you can see, if we're still using mean squared error to calculate where our model will perform best, then we can see that as alpha increases or decreases, then this can actually blow up this term, not this term right here, but rather this entire term right here is just going to blow up. Right? Let's say alpha is equal to 100. Okay? Depending on the weights, let's say you have some value in the weight matrix that was pretty large. Let's say it was 20. Okay? This term, when you multiply the two together, alpha and times the weight matrix, it's going to be a huge value, right? But understand that this is not something that occurs in nature, right? Nature will not make this value a part of your training set, right? It's just something we artificially tag on top of it, but in your actual data set, the information that you train off of, this would never be accounted for. And so if this term blows up, then the amount of error that you're going to have in your prediction once you compare it to your ground truth value, the error is going to be huge. Okay? And so we'll choose, in other words, calibrates our model based off of that alpha value. It's something that we choose. Folks call that a hyperparameter. We choose an alpha to determine how much to just blow everything up based off of the weight matrix. And so in turn, the effect that it has on our model is that it tries to minimize the weights, right? We could set alpha to some huge number. Let's say it was 10,000, right? That means if we want this entire equation to be as close to what actually occurs in nature, that means the resulting weight matrix has to be really small in order to counteract the effect that this 10,000 has. We want this term to be basically non-existent when we're comparing the predicted value to the ground truth value. Okay? So that technique, as you'll see in all kinds of machine learning, is called regularization. Okay? Regularization is used to control our weight matrix just a little bit more or a lot bit more. It's an additional constraint that we put on our model, which allows the model to actually learn more based off of less data. If we just have a small amount of data, we learn not only based off of the training data, but we learn based off of our penalty that's caused by large values in the weight matrix. Okay, so the last note here, increasing alpha enforces a tighter restriction on the model. Like I just said, if alpha is set to 10,000, then this entire term is going to blow up. So if we don't want it to blow up, our weight matrix either has to be smaller during training or we need to decrease our alpha value. So hopefully that gives a clear, brief introduction to ridge regression. And in the next video, I will do a comparison between the trade-offs of ridge regression compared to linear regression.